Imagine standing in a place where gravity seems to defy the laws of physics. From mysterious areas where cars roll uphill to bizarre spots where objects float in midair, there are some places in the world where gravity doesn't seem to work as it should. But first, we need to understand what gravity actually is. What is gravity? Put simply, gravity is one of the most fundamental forces in the universe. It controls everything from the movement of planets, stars, galaxies, and even the trajectory of light. Even though it is the weakest of the four fundamental forces of nature, gravity's effects can be felt over vast distances, and it influences the behavior of all objects with mass. It's what keeps the large-scale structure of the universe together, and it keeps the planets in orbit, and it's why we remain firmly on the ground. But there are a number of things that affect how strong it is. Let's talk about the basics of gravity. Gravity is defined as being the force of attraction between two masses. The larger the mass of an object, the greater its gravity. Distort the fabric of space-time, and they create a well that other objects can fall into. Smaller objects like spacecraft or human beings move along the curves in this warped space-time, which we perceive as gravitational attraction. For example, the Earth orbits the Sun, not because the Sun is pulling it with a force, but because the Sun's mass curves space-time in such a way that the Earth follows a curved path around it. The best way to think about this is by imagining a heavy ball placed on a stretched-out sheet of fabric. The ball will create a dent around it in the center, and smaller objects, when they're rolled onto the fabric, will move towards the ball because of the curved surface. It's this theory that also predicts strange phenomena like gravitational time dilation, where time moves slower in stronger gravitational fields, gravitational lensing, where gravity can bend light, and the existence of black holes, where gravity is so strong that not even light can escape. How about some things that affect gravity? Well, there are 6 main factors that will interact with us. This is why if we set foot on Mars, where the gravity is weaker, we would weigh less. Number 2 is distance. The further two objects are away from each other, the weaker the gravitational force is between them. This is because gravity follows what's known as an inverse square law, and this means that if you double the distance between two objects, the gravitational force between them is reduced fourfold. This is why astronauts in orbit, such as on the International Space Station, will experience microgravity because they're far enough from Earth's center that the gravitational pull is much weaker, but it's not gone altogether. 3 is the distribution of mass. The way that mass is distributed within an object can also influence gravitational effects. A spherical object like a planet has a gravitational field that acts as if all the mass were concentrated at its center. In reality, though, this mass is unevenly distributed, such as in mountains, ocean basins, or underground structures. And in these places, there can be local variations that are known as gravity anomalies, because of the difference in gravitational pull that's being exerted by one object on different parts of another. For example, the Moon's gravitational force on the Earth is what causes tides, as the side of the Earth that's closest to the Moon experiences a stronger gravitational pull than the side that's farthest away from it. In a similar way, as well as holding the Moon in orbit around the Earth's gravity exerts tidal forces on the Moon. This causes its rotation to synchronize with its orbit, and this is why we always see the same side of the Moon when we look at it. Number 6 is relativistic effects. While it's not something that we experience, or at least perceive from the Earth, in a very strong gravitational field, time slows down and space is curved. These effects are most clear near massive objects like black holes or neutron stars. For example, near the event horizon of a black hole, gravity is so strong that space-time becomes infinitely curved, and any object falling into it will appear to freeze in time from the outside if you're looking at it differently. Mount Nevado Huascaran in Peru. Mount Nevado Huascaran is in the Cordillera Blanca range of the Peruvian Andes, and as well as being the highest mountain in Peru, it's also the highest point in the tropics with an elevation of 22,000 feet, or just over 6,700 meters above sea level. This combination of height and its position mean that it's a place where gravity can noticeably be measured to behave slightly differently from what we experience at sea level. The peak of the mountain is so far from the center of the Earth that according to the inverse square law of gravity, the gravitational pull will be weaker than at lower altitudes. This works in combination with the fact that the mountain is close to the equator, and as the Earth bulges around the middle, it puts the peak even further away from the center than an equal height mountain would be somewhere else. This all means that Nevado Huascaran has some of the weakest gravitational pull on Earth, and a person standing at the summit would weigh slightly less than they would at sea level. Scientists have calculated that the gravitational acceleration here is around 9 point. They must carefully acclimatize to the environment. Hudson Bay in Canada. Covering an area of 470,000 square miles or over 1 million square kilometers, Hudson Bay, which is in northeastern Canada, is a huge geographic feature that's been important for local communities for thousands of years. More recently, though, scientists have discovered that it's also the site of a gravitational anomaly. And to begin with, no one had any idea why. It was found that in this region the force of gravity is slightly weaker than in other parts of the world, and while the difference is tiny, seeing a reduction of 1/5000% is still significant enough to have drawn the attention of geophysicists, looking to explain why gravity is behaving differently in the Hudson Bay area. Following an extensive study, the gravitational anomaly is now mostly thought to be down to two main factors: post-glacial rebound and the presence of the Laurentide ice sheet during the last ice age. These geological events were crucial in the formation of this region's landscape. Crust began to slowly recover. This process, however, is still ongoing, and the crust is not yet fully returned to how it was before the ice age. This slow rebound creates a subtle but measurable difference in gravity because the mass of the Earth beneath Hudson Bay is still displaced compared to other regions. The Laurentide ice sheet had another major effect on the region too, because it displaced a huge amount of mass from Hudson Bay. When the ice melted, it left behind an area that is less dense than surrounding areas. This difference in density affects the distribution of Earth's mass, and as a result, the gravitational pull. Essentially, the gravitational force in Hudson Bay is slightly weaker because there's less mass beneath the surface compared to other parts of the planet. Alright, how about Chimborazo in Ecuador? If you were asked where the farthest point on land from the center of the Earth is, most people would probably guess the peak of Mount Everest because it's the tallest mountain in the world. Well, due to our planet's shape, though, this isn't actually correct, and the true answer is the little-known Mount Chimborazo. The effect makes such a distance that, despite being around 8,500 feet or 2,600 meters shorter than Mount Everest, the peak of Chimborazo is actually around 6,500 feet or 2,000 meters further away from the center of the Earth. This increased distance from the Earth's center at Chimborazo's summit directly affects the gravitational force that's experienced there. Again, because of the inverse square law, studies have shown that the gravitational acceleration up there is about 9.763 meters per second squared, compared to the average of 9.8 meters per second squared. And that would be enough to make you weigh slightly less and put some added pressure on your body to function in the same way as it does at lower altitudes. Chimborazo's gravity anomaly is important to know about and to measure for researchers in the field of geodesy, which is the science of measuring the Earth's shape, gravity field, and surface. They can use the data from places like here to refine models of the Earth's gravitational field, which is important for our satellite navigation, geophysics, and understanding the planet's internal structure. Bangui in the Central African Republic. Bangui is the capital of the ground-based studies, which revealed that the pull here in this area is significantly higher than in surrounding regions. There aren't any of the geological formations you would usually look for in cases like this, like large mountains or dense rocks, and it's particularly surprising because the region around Bangui is relatively flat and geologically stable. There are no major tectonic plate boundaries, significant volcanic activity, or dense mountain ranges that would usually be linked with a heightened gravitational force. The leading theory right now for this anomaly is that the area might sit on top of a previously undiscovered and completely buried impact crater, which could have been caused by a large meteorite strike that happened millions of years ago. Meteorite impacts compress materials in the Earth's crust and would result in a concentration of denser rock materials beneath the surface. This theory is supported by the fact that the anomaly is circular, which is consistent with the shape of impact craters elsewhere found on Earth, or variations in the Earth's mantle, where hot, less dense material rises towards the surface and has complex interactions with the surrounding rock. This explanation is seen as less likely, though, because mantle plumes are usually associated with volcanic activity, which is not present in this region. Let's take a look at the Indian Ocean gravity anomaly. The Indian Ocean gravity anomaly is another one of those more mysterious gravitational ones on Earth. It's found in the central part of the Indian Ocean. This region has an unusual deviation from the expected gravitational field, where gravity is significantly lower than it should be. This anomaly is found south of the Indian subcontinent and north of Antarctica, and it covers a large area of the ocean where the gravitational pull is weaker than in the surrounding regions. It's an area where the Earth's gravitational field dips by more than 100 milligals, which is a unit used to measure gravitational variations, compared to what would be expected based on the local topography. Essentially, something below the surface is creating a lack of mass or a different distribution of mass. Another suggestion is that the anomaly is caused by the remnants of ancient tectonic plates or subducted slabs of oceanic crust that have sunk deep into the Earth's mantle over millions of years. These sunken slabs could have altered the mass distribution below the surface and affected the gravitational field above. Some scientists think that the remains of ancient Tethys ocean plate, which moved beneath the Eurasian plate, might still be within the Earth and contributing to the anomaly. Because of the potential to learn more about the Earth's mantle, the Indian Ocean gravity anomaly continues to be an area of active research. Modern satellite technology, such as data from the Gravity Recovery and Climate Experiment mission, has provided more detailed insights into the Earth's gravitational field here, allowing scientists to map the anomaly with greater precision, and hopefully one day be able to explain it. The Great Rift Valley in East Africa. The Great Rift Valley is one of the most geologically active regions on Earth. It's known for its tectonic activity and stunning landscapes. It covers a distance of 3,700 miles. As a result, the Great Rift Valley has a unique distribution of mass beneath the surface. One of the most important factors that contribute to the lower gravity in parts of the Great Rift Valley is the presence of the Rift Valley and deep depressions. These low-lying areas, such as the Danakil Depression in Ethiopia, are formed as the Earth's surface stretches and sinks. The reduced mass in these valleys leads to a weaker gravitational pull, and things are then made more complex by volcanic activity. Interestingly, the gravity in the Rift Valley doesn't behave the same across the entire region. While many parts of the rift experience weaker gravity, there's also areas where gravity is slightly stronger, such as the Ethiopian highlands and Mount Kilimanjaro. The South Atlantic Anomaly, or SAA, is a region where the Earth's magnetic field is significantly weaker compared to other areas, stretching from South America to the southern Atlantic. This anomaly is mainly known for its effects on our planet's magnetic field, but it also has connections to gravitational variations in the area. It's a region that's become important. Space that are trapped by Earth's magnetic field comes closest to the Earth's surface, exposing satellites and spacecraft to higher levels of radiation. As a structure beneath the crust is enough to affect the magnetic field, then maybe it's no surprise that there are gravitational anomalies too. In the South Atlantic, some studies have suggested that these could be related to mantle convection, where this convection current of molten rock in the mantle caused variation in the distribution of mass beneath the Earth's surface. But the SAA region doesn't have large changes in gravity like some other locations like the Hudson Bay gravity anomaly or the Great Rift Valley, but scientists have detected small variations in the gravitational field using satellites. Researchers think that this could be linked to the South Atlantic tectonic plate and its interaction with the surrounding plates. Most of the tectonic plates can cause changes in the density of the Earth's crust, which in turn leads to small variations in the gravitational field. As well as this, the slow movement of molten material in the mantle beneath the SAA could be influencing both the magnetic field and the gravitational anomalies. The Chicxulub crater, which is on the Yucatan Peninsula, including non-avian dinosaurs. It's obviously then a huge, historically significant place, but studies have shown long-lasting effects of the impact too. as the Chicxulub crater also has some interesting gravitational anomalies. After such a massive event, the area around the crater shows measurable variations in gravity due to the differences in density. Studying the Chicxulub impact crater isn't easy. After tens of millions of years, it's now buried beneath layers of sediment. In fact, gravitational measurements are one of the most effective tools to fully understand its structure. After an impact of such magnitude, the distribution of mass in the Earth's crust was changed, and this has created areas with both higher and lower gravitational forces. Within the Chicxulub crater, there is a noticeable negative gravitational anomaly at the center of the impact site. This means that gravity is slightly weaker. The asteroid's impact displaced massive amounts of rock. The South Pole in Antarctica is one of the coldest and remote places on Earth, and while it's mostly known for its role in the planet's magnetic field, it does have some unique gravitational characteristics too. Found at the southernmost point of Earth, these differences in gravity are the result of a combination of factors, including its location on the planet, the thickness of the Antarctic ice sheet, and the shape of the Earth itself. At the South Pole, gravitational acceleration is around 9.83 meters per second squared, compared to the typical 9.8 meters per second squared at sea level elsewhere on the planet. It is a small difference, but it means that you would weigh slightly more at the southern pole, and there would be a slight effect on your body's cardiovascular system. Another thing that affects gravity at the South Pole is the Antarctic ice sheet, which is the largest ice mass on Earth and contains around 60% of the planet's fresh water. The sheer volume of ice creates a gravitational anomaly because of the massive amount of frozen water that adds significant mass to the region. More mass means a stronger gravity, so gravity here is slightly stronger than it would be. Rock formations or thicker sections from the Earth's crust exert a slightly stronger gravitational pull, while regions with less dense materials create weaker gravitational fields. Now let's take a look at places where gravity is an illusion. The reverse waterfall of Nanagat, India. So, the reverse waterfall at Nanagat in India is a natural phenomenon that, at first, appears to go completely against how you'd normally expect water to behave under the force of gravity. The site attracts visitors from all over the world who come to see the water flowing upward rather than cascading downward. While it might look as though gravity is reversed here, the reverse waterfall is, however, an optical illusion created by the local landscape. Nanagat Mountain Pass was historically used as a trade route between the Konkan coast and the Deccan Plateau, and it's long been a popular place for its scenic views. During the monsoon season, the Western Ghats experience heavy rainfall, and countless waterfalls begin to flow over the cliffs and hillsides in the region. It's relatively low volume compared to larger waterfalls, and it's more easily caught by the powerful wind. The reverse waterfall effect, though, is most pronounced during the peak monsoon season when both rainfall and wind speed are at their highest. During this period, the waterfall produces fine mist and droplets, which can be blown far back into the air, making it appear as though the waterfall is suspended or flowing in reverse. How about the Mystery Spot in California? The Mystery Spot in Santa Cruz, California is one of the most famous roadside attractions in the US, and it's known for its unusual optical illusion. Located in a redwood forest, the area is just 150 feet or 46 meters in diameter, but has completely baffled people ever since it first opened to the public in 1940. It's described as a place where the laws of physics and gravity seem to operate differently, creating a series of strange effects that leave people questioning what they see and feel. As you enter the Mystery Spot, you straightaway notice that many visitors simply walking through the cabin makes them feel dizzy, their bodies struggling to make sense of the visual information they're receiving with their own sense of balance. While the effects at the Mystery Spot may feel supernatural or mysterious, they are of course the result of cleverly made optical illusions and the site's unique construction. The entire area is built on a steep hill, and the tilted cabin is built at an angle that confuses visitors' perception. As a result, the brain misinterprets visual cues about the angles and slopes, making people feel as though they're leaning or standing at impossible angles. Over the years, though, not everyone has looked for the simplest explanation for what happens here, and have instead put forward other ideas about what makes it such a mystery spot. Some have believed that it's a true gravitational anomaly or underground geological formations, like deposits of iron ore or even alien activity, are responsible for these strange effects. The Mystery Spot remains a popular tourist destination, as it's been there for more than 80 years.